Let's get started with lecture 21. So last time we talked about how stand-in waves can be constructed using reflection from boundaries, right? So stand-in waves needed two counter-propagating traveling waves with the same, let's say, amplitude and frequency. And one way to construct these is to have a boundary in our system. So you send one wave and then it gets reflected from the boundary. And then the incident wave and its reflection or the reflected wave interfere and can create stand-in waves in our, let's say, string. So we talked a little bit about the boundary conditions. So in particular, we had fixed boundary conditions. Right, the string is just attached to some fixed point that doesn't move. So that means that at that point, the displacement is always 0. And then we can have, let's say, free boundary conditions. So one way to construct it in a string system is to have like a frictionless loop that can freely move up and down a rod. And then this boundary condition, for reasons that we discussed, gives us that derivative with respect to x, which is basically the slope of this tangent to the string at that point, for all times is 0. Right? These are, of course, they also have position dependence, but it's just at that point. So let's say, for example, if that's x equals 0, this is x equals 0, it's at x equals 0, and that's only at x equals 0. Okay? So then we talked about now what are the frequencies for which we can have stand-in waves with different boundary conditions. And to summarize what we discussed, we have two scenarios. So we either have fixed or free, or we can have fixed, free, fixed. So as an example, let's just draw the fundamental wave, fundamental stand-in wave. That's the one with the longest possible wavelength, the shortest possible frequency. So if it's fixed, then we would just fit 1/2 of a wavelength in there. And if it's free again, we would fit 1/2 of a wavelength. It looks different, but the length is lambda over 2. The length of the string will be lambda over 2. So let's draw the free here. So again, that's 1/2 of a wavelength. Say from a minimum to a maximum. So in both these cases, L becomes m times lambda over 2, where m is 1, 2, 3, etc. I can draw the next one. So these are for m equal 1. If I draw the next one for m equal 2, I fit 2 lambda over 2's here inside my string. So again, that's m equal 2 here. And similarly, so that's 1 lambda, and this is 1 lambda, right? It goes from maximum to the maximum, right? So that's also m equal 2 for free. So we find the same expression for our allowed wavelength. Let's call them lambda m. The wavelength depends on this integer m. And then if we solve for the frequency, we find, let's say, so lambda m fm is v, the speed of the propagation. So fm becomes v over lambda m. And let's write one more equation. Lambda m from here is 2L over m. So that becomes 2LV over, excuse me, this V over lambda. So 1 over lambda is m over 2L. So that's going to be mv over 2L. Okay, so we see that the allowed frequencies for the fixed, and free is the same. They depend on this integer m. And of course, the fundamental frequency is the smallest one. F1 is V over 2L. That corresponds to this case for m equal 1. Now, the fixed free or free fixed, again, they're just a mirror image of one another, right? So, for example, fixed free, let's say fixed is on this side, free is on the other side. It's going to just look like this. Right. So you have a node here, you have an antinode there. So here, L is lambda over 4, right? A quarter of lambda fits inside. And yeah, you can switch. It doesn't matter, right? If the fixed boundary is on this side and free is on this side, again, one finds the same thing. So now the node is here, the antinode is here. So in general, we found that to have this picture, we have 1 lambda over 4, and then to get the next node, we have to add an integer multiple of lambda over 2, right? So let me draw the next one, for example. 1 lambda over 2 here, and then the lambda over 4 is over here. So that gives an odd multiple of lambda over 4, right? You have lambda over 4 plus 1 lambda over 2, which is 2 lambda over 4. So that's 3 times lambda over 4. Here we had 1 times lambda over 4. So Lm in this case is m times lambda over 4, but m is not all integers. It covers the odd integers. So it can be 1, 2, 1, 3, yes, 1, 3, 5, etc. 1, 3, 5, 7, etc. All right. So the frequencies, again, can be extracted from these wavelengths, right? So we can solve for the allowed wavelength. But it's really important to remember what values these m's take, these integers take. So here this becomes, L is this. L is m times lambda m over 4. So lambda m becomes 4L over m. And the frequency becomes, again, it's v over lambda, so it's m v over 4L, where m is, again, 1, 3, 5, etc. And of course, for waves on a string, like in the case of musical instruments, like a guitar, the most common scenario is the fixed boundary condition, right? It's much easier to just pin down the string at some point. This was a little bit kind of a mathematical construction. So these like free boundary conditions for string for strings are not very common. They're extremely common when we talk about sound waves. So we're going to talk about that later. All right. So I think at this point it's good to maybe look at an example. All right, so here's an example. It's problem number 17.8 from the end of the chapter. So there are two parts. Part A is saying what are the three longest wavelengths for standing waves in string of length 240 centimeters with both ends fixed. And part B is saying if the frequency of the second longest wavelength is 50 hertz, what is the frequency of the third longest wavelength? So pause the video, try to work out the solution to this problem. Okay, so I hope you managed to find the correct answer. So let's see. So first, let's think about part A. That's the easy part. So what are the three longest wavelengths, right? So the first one is this one, right? Is the fundamental mode. So we just fit half of lambda in the entire length. So therefore lambda is twice the length. So it's 2L. It's 480 centimeters. Right, from here to here we have 240. Lambda is twice this. Then the next one, as you can see, has 2 lambda over 2, so lambda is equal, so let's call that lambda 1. Lambda 2 is just L, which is 240. And then the next one will have 3 lambda over 2's inside the length, so lambda 3 will be this divided by 3 basically. So 480 divided by 3 is 160 centimeters. Okay, so that's the answer to part A. It just depends on length. And then part B is saying if the frequency of the second wavelength, so this guy, if this has f2 equal 50 hertz, what is the frequency of the third longest wavelength? So this guy, what is f3? Right? Okay, so how should we proceed? Well, we know that the speed is the same. It's the same string. So it has the same tension, same linear mass density. It must have the same speed. So we just need to figure out the associated frequency. So let's say we have f2 lambda 2 is v, so is f3 lambda 3, right? Therefore f2 lambda 2 is f3 lambda 3. We just set the v's equal to each other, and f3 becomes lambda 2 over lambda 3 times f2. So lambda 2 over lambda 3 is 240 divided by 160, so that's 24 over 16, which is 1.5. So of course this is times f2, so this is 3 halves f2. F2 was 50 hertz, so that should be 75 hertz. All right, it has a shorter wavelength and then higher frequency. Okay. Also solve this a different way. You can just maybe solve for v, right? If you know, you know f2 and you know lambda 2, so you can multiply them, find v numerically, and then divide it by your lambda 3. Or one can also find it more directly kind of using our equations. That's another way. So we know Fm in this case is mv over 2L, right? V is mv over 2L. So therefore F3 over F2, we immediately see V and L are the same, so it's going to be 3 over 2, right? And so we find that that's a more direct way, not worrying about lambdas, just using the equation for the frequency. So you have different ways to solve this problem. All right. So let's now talk about longitudinal sound waves. So the analog of a string that's under tension is just a long, narrow column of air. So imagine the air in a tube or a pipe, right? So you can't have one-dimensional longitudinal sound waves in this confined geometry. Generally, sound waves propagate in three-dimensional space, right? You have a sound source, you get like spherical wavefronts. But if the air is confined in a narrow, long tube, it's basically a quasi-one-dimensional universe for the sound waves, and they can just propagate back and forth inside it. So that can support these one-dimensional longitudinal sound waves. And now, if the end of this tube is closed, right, then the air molecules there cannot move. So that gives a node in displacement. And if the end is open, then the air molecules are free to move. So it's the analog of the free boundary condition. So it gives an antinode. So let's say, switch gears a little bit here, talk about longitudinal one-dimensional sound waves. So if you have a tube and you close the end, displacement node, right? The air molecules here really cannot move that way. They hit the wall and cannot move. And if you have, let's say, so similarly this end, but if you have an open end like this, they're completely free to move, so you get a displacement antinode. Now, there's something quite interesting about sound waves is when they hit the wall and they cannot move, pressure builds up there. So you're gonna get a maximum. You're gonna get the maximum pressure there. So a displacement node corresponds to the highest pressure. So it becomes a pressure antinode. And similarly, this open end, there's no pressure, right? The pressure is the same as that was the pressure of the atmosphere is the same as the outside pressure. So there's no reason for pressure to build up. The molecules can move freely. So this corresponds to a pressure node, right? Relative to the pressure of the atmosphere, there's no extra pressure. So if you measure the pressure with respect to the pressure of the atmosphere, then there's zero extra pressure. So it becomes a pressure node. So let's take a look at that one example. So this is the case where you have two closed ends, and then the displacement is 0 here and here, and this is the m equal 2 sound wave here. And see, you have pressure antinodes here, right? So you have, let's say they've moved to the center, so there's compression at the center, there's rarefaction close to the boundaries. So yeah, so that's a bigger change, right, relative to some uniform gas at the boundaries. The pressure, you know, can be both positive and negative. It's the antinodes have to do with the amplitude, right? It's a constantly fluctuating quantity. So yeah, so that's without any displacement, right? Where all the displacement is zero, you have this uniform pressure, and if the density is the same as the density of the air outside, it's just the atmospheric pressure outside. So now, as the displacement changes, right, so these displacements become negative, these become positive. So previously, let's say we had positive here, right, so that's why you have compression in the middle. The molecules over here have moved this way. Now, as this fluctuation goes on, you know, now you have compression here. Here you have lower density. But again, the peaks of pressure occur at the boundary, right? So here you have positive pressure. Here you have negative pressure, but both of them have the largest amplitude. So that's this kind of dual picture, thinking about either the displacement of molecules, like here, so that's delta x, let's say, graph as a function of position, so this is the second mode. Or we can think about the pressure wave. So basically for pressure we have two antinodes at the ends, and then this antinode must be a node, so a node here must be an antinode. So we see the wavelength for the pressure is the same as the wavelength for displacement, right? So here we fit one full lambda. Here it's also one full lambda, right? You go from one maximum to another maximum. So it's basically the same thing, right? When we had the waves on a string, we argued that the frequencies and wavelengths are the same for both free and fixed boundary conditions. And so closed ends are fixed boundary conditions for displacement, and they're free for pressure, right? They give us the highest possible pressure there because you really stop the molecules from moving and pressure builds up. Okay, so let's think about this example together. So singing in the shower. So we have a shower stall that's 8 feet tall, and for what frequencies less than 500 hertz are there standing sound waves in the shower stall? So we imagine it's kind of a narrow shower, right? It's and you're standing there and it's tall, so the approximation is we can approximate it by column of air that's 2.45 meters or 8 feet long. And of course there's the floor and there's the ceiling, so that gives closed ends for this shower. The assumption is that it's not an open outdoors shower. There's a ceiling and there's a height of 8 feet. So then there must be nodes at the ceiling and the floor. So so M2 looks like this, right? Just rotated. It's just the column is now vertical, but take the whole thing and rotate it. So let's say this is the floor, this is the ceiling. So we can first calculate the fundamental frequency. F1, remember, is mv over 2L. It's exactly the same math as standing waves in string. So we know the speed of sound in air at usual temperatures like 20 degrees Celsius, for example, 343 meters per second, divided by 2 divided by the length. So 70 hertz is the fundamental frequency. Okay, so then our formula was Fm is m times v over 2L. So we just have all these frequencies, 70, 140, which is twice that, 3 times that. And finally we go to mode 7, right? 7 times 70 becomes 490, and then the next one will be 560, which is above 500. So we just found all the frequencies. And of course, the fact that there are many natural frequencies for standing waves inside this tube means that there are many resonances, right? So there are many frequencies where kind of your voice can get amplified because it resonates, and yeah, that's the reason many people enjoy singing in the shower. All right, and of course the caveat is that, of course, this approximation of a one-dimensional tube is not that realistic. Okay, so we talked about the closed case. Displacement looks like this. Nodes in displacement. And closed, like physically closed tubes, corresponds to free boundary conditions for pressure. So pressure has antinodes at the boundaries, and then that's m equal 1 mode. That's how it looks like for displacement, and pressure m equal 2 looks like this, m equal 3 looks like that. So yeah, so thinking about displacement, it's really like the displacement of a standing wave in a string, right, with fixed boundary conditions. And the pressure in this case, in the closed case, looks like the displacement for free boundary condition of a string, which we discussed before. Similarly, you can play this other game, consider the open. Now for open, kind of pressure and displacement switch, right? So now pressure has nodes, so it looks like the fixed situation of the string, and then displacement has antinodes, so it looks like free boundary condition. And as we discussed in the case of the string, you fit the same number of lambda over 2s. You fit an integer multiple of lambda over 2, right? Here, from here to here, we have lambda over 2. Also from here to here, going from maximum to minimum, that's also half the wavelength. So we find the same expressions for the frequencies and the wavelength as the closed case. Finally, there's open closed case. Right, so now the pressure here has antinodes, here has nodes. Displacement is doing the opposite. And see, this looks like what we found for the fixed free boundary condition in the string, right? So it's going to be an odd integer multiple of v over 4L, right? We're going to fit a lambda over 4 plus an integer number of lambda over 2s, which becomes an odd integer multiple of lambda over 4. All right. So here's a quick question. Pause the video, try to figure out the answer. Okay, so both ends are open, right? So it belongs to the open or closed case, like the same boundary condition. And in that case, we fit an integer number of lambda over 2s, right, inside inside the tube or inside the system. And that integer doesn't have to be odd, right? So when we have different boundary conditions, when it's either open, closed, or closed, open, we fit an integer multiple of lambda over 4 inside it, and that integer has to be odd. In this case, or in the closed case, we fit an integer multiple of lambda over 2, and that integer doesn't have to be odd. Okay, so now m equal 3 means we fit 3 lambda over 2s, right? So the length L must be 1.5 lambda. All right, so that's one piece of information. The other piece of information is this is what is it? This is a displacement graph, and we have open ends. So for open ends, the displacement must have antinodes, right? For closed, it has nodes. For open, it has antinodes. So A and C are incorrect. They have nodes at the ends. We don't want them. So the correct answer is either B or D. Okay, so let's just see what the length is. So I start from here, go all the way down, reach the maximum. That's 1 lambda. That's 1 full wavelength, 1 full cycle. And then from maximum to minimum, that's half a lambda. So that's 1.5 lambda. That's good. That's the correct answer, right? 3 halves. I fit 3 lambda over 2s inside my tube. This one wouldn't be correct because this is 1 lambda from here to here. This is another lambda. So 1 lambda from here to here, another lambda from here to here. So this seems to be 4 lambda over 2s, right? So L in this case is 2 lambda. So we don't want that. We want 3 lambda over 2s. All right, what about this one? So this is a different case. Again, pause the video, try to figure out the answer. So we have an open closed tube, length L. So which is again the correct displacement graph for the m equal 3 standing wave. Okay. So now we have different boundary conditions, right? Here it's open, here it's closed. So now we have an odd multiple of lambda over 4 inside our tube. So that's one piece of information. The other piece of information is here is open, so the displacement must have an antinode. Here is closed, the displacement has a node. So it's either B or D, right? These ones, A and C, have the wrong boundary conditions. So let's look at B. So how many lambda over 4s are in there? This is 1 from here to here, from maximum to 0. And then that's another full lambda, so that's 4 lambda over 4. So that's 5 lambda over 4s. That doesn't work, right? We want 3 lambda over 4s. M is equal to 3. And this works, right? This is lambda over 4. This is lambda over 2, so that's 2 lambda over 4s. We have a total of 3 lambda over 4. All right, let's work out another example. So this is problem 1720 from the end of the chapter. So the question is, a violin string is 30 centimeters long, and it sounds the musical note A, which has a frequency of 440 hertz, when played without fingering. So the total length of the string is involved. The question is, how far from the end of the string should you place your finger to play the note C with a frequency of 523 hertz? All right, so how should we proceed here? So one kind of important piece of information is that typically musical instruments, the sound they produce is the fundamental frequency corresponding to standing waves in them. So if it's a string, it's closed or fixed boundary condition, and the dominant sound is the fundamental frequency associated with that, which has the property that L is lambda over 2. And then for wind instruments, we can have both open and open closed boundary conditions. And again, the associated fundamental frequency is the dominant sound that they produce for a given, let's say, height of the column of air inside that tube. All right, so in the case of the violin, we know that, let's say, this is 30 centimeters from here to here, and if it produces the fundamental frequency, well, it looks like that. So lambda is 60 centimeters, so lambda 1, let's say, 60 centimeters. So that's associated with a frequency of 440 hertz. So F1 associated with that is 440 hertz. So now if you place your finger here, so if I, let's say, pinch down this point, some length x here, or let's say x here, then this part of the string effectively, so now here where I put my finger, I create another fixed boundary condition, right? I don't let the string move there. So now it's going to be this fundamental frequency when you place your finger at distance x from one end of this wire. Now, let's say this lambda, well, we don't know what it is, but it's 2x, right? In the same way that this lambda was 2 times 30, the whole length of the string. And the frequency associated with that, because we know it plays the note C, is going to be 523 hertz. So we want to see what x is. And this is relatively straightforward, right? So we don't know the speed, but we know that lambda f is the speed. So we can solve for speed from there, and we also have lambda f is the speed, and then put it in, solve for x, or we can just eliminate the speed and say 2x times 523 is 60. So we're going to get our x in centimeters this way because we put centimeters there, times 440. And then x becomes 30, right? 60 divided by 2 times 440 divided by 523. That's in centimeters. So whatever that number is, we can put it into a calculator. That's where we should place our finger to produce the note C on a violin. Okay, let's take a look at another example. So we have a clarinet that's 66 centimeters long, and we have a flute that's the same length. All right, so what are the frequencies of the lowest note and the next higher harmonic? So lower note means lowest frequency, largest or longest wavelength on a flute and on a clarinet. And the speed of sound in warm air is 350 meters per second. So the model is that the flute is open. So open at the end as well as the hole the player blows across, and a clarinet is open-closed because the player's lips kind of seal the tube. Okay, so that's the difference between the two, at least in this simple model. Okay, so pause the video, try to work this out. All right, So yeah, so the length is 66 centimeters. So let's go here. Example 17.6. So let's say this is the flute, and this is 66 centimeters. That's again 66 centimeters. All right, so we want to know the two lowest frequencies, right? That these two musical instruments play, and we know we want to know their frequencies, and we know the speed of air is 350 meters per second. So let's say V is 350. Okay, so what should we do? Well, so for the flute, the lowest one will look like this, right? We need to have antinodes here and here. So the lowest one will look like this. So L must be lambda over 2. If it's an integer multiple of lambda over 2, if we have the same boundary conditions, right? So that's fine. And then the next one is going to be 2 lambda over 2, right? It's just m times lambda over 2. So L is that. For the next one, let's also draw that. We already know the answer from the equation, but it looks like this, right? So now this is 1 full lambda, right? We start from a minimum, reach the next minimum. So L is lambda, which is 2 lambda over 2. Okay, so that's the case of the flute. And L is, of course, 66 centimeters. So for the clarinet, for the lowest one, here I have a node, and I'm drawing the displacement. Alternatively, I could have drawn the pressure, which replaces, antinodes with nodes and nodes with antinodes. So it would look like this. Let's say that's the pressure here. But it would give the same result. So for the clarinets, let's say I have a node here and an antinode there. So the largest frequency, L, is lambda over 4. And then we know what happens, right? We have different boundary conditions, so we're going to fit an odd multiple of lambda over 4. So the next one is going to be 3 lambda over 4 from the equation. And just visualizing it, well, I have to just put in the next node. So that's lambda over 4, that's lambda over 2, it's 3 lambda over 4. All right, so we want to find the associated frequencies to all of these cases, right? So from here, lambda is 2L. From here, lambda is L. From here, lambda is 4L. From here, lambda is 4L over 3. Now, frequency, right? What's the relationship? We know F is V over lambda. So V over 4L, V over 3V over 4L, V over 2L, V over L. So then we just plug in numbers, right, in all the cases. So 350 times 2 times, let's say, 0.66, and that's in hertz. So whatever that number is. Similarly here, this becomes 350 over 4 times 0.66. That's in hertz. This is 350 over 0.66. And this is 3 times 350 over 4 times 0.66 in hertz. All right, so let's take a look at the solution here, which has the numbers we would get from a calculator. So yeah, so for F1, for open, we have V over 2L. In this case, we have V over 4L. Yeah, those are the numbers. And then the next one for the open is twice it, right? We fit 2 lambda over 2's, right? The m can be any integer. But for open-close, m must be odd, so we're going to get a factor of 3 times the fundamental frequency. Okay. All right. So this is a good place to stop, and next time we'll continue this discussion talking more about the mathematics of interference in 1 dimension and higher dimensions.